Hi everyone, my name's Ben. I'm going to be talking about physical computing with Python and Raspberry Pi. So this is me. I work as community manager at the Raspberry Pi Foundation. I work on various different programs and doing outreach activities, some software and project development, and I write learning resources for children, and we do some teacher training programs as well. I used to be a hobbyist into Raspberry Pi things in the early days, and I was hired to join the team. Moved to Cambridge in the UK, and I've been working for them for about 2.5 years. I'm Ben_Nuttall on Twitter. So this is Raspberry Pi, so I've got one here. It's a $35 credit card size computer, single board computer. With the Raspberry Pi Foundation, we're an educational charity. We were founded about 10 years ago. The way we work is that we operate as a charity that owns a trading company. So the Raspberry Pi trading company makes and sells Raspberry Pis and has licensees that pay a license fee for every Raspberry Pi they sell. All the money comes into the Raspberry Pi trading company, which is owned by the charity, and that's how we fund our charitable programs, our educational programs. So the reason kind of Raspberry Pi came about was looking back to 1981 when this was what a computer looked like. And anyone who got the chance to have a go on one of these computers ended up, whether they intended to or not, they had to learn some programming skills to be able to use this computer. And then in 2010, this was what a computer looked like. And you're in a position where there's virtually no programming necessary to do most general tasks, as everything's wrapped up in this kind of graphical user interface. So we wanted to make something more bare bones and go back to basics to give people a chance to do interesting things with computers, learn programming skills, learn how computers work, and do some interesting stuff with them. So they came up with some prototype devices that look something like this, and they settled on the original Raspberry Pi, which looked like this. So when this came out in 2012, this was the Raspberry Pi Model B. It was a 700 megahertz ARM core, a 32-bit CPU with a video core 3D graphics processor and 1/4 gig of RAM. Cost $35 and sold out quite quickly and sold quite well for the first year or so. We moved on to further models as well, but in the meantime, lots of Raspberry Pi community activity was going on. So people were writing books about Raspberry Pi. People were making accessories, cases, add-on boards, writing about Raspberry Pi in magazines, and that sort of thing. And people were also getting together at these Raspberry Jam community events where people of all ages would meet up and teach each other, learn from each other, share their projects, share their skills. And it'd be a good place for anyone, whether they're young or older, to learn new skills through these community events. And these have been really successful. They've been running since the early days. Raspberry Pis are kind of spread around the world, so there's a big concentration of them in the UK and quite a lot in the US, but there's a few around the world as well, and we're working to support the growing network of these Raspberry Jams around the world. I'll talk more about that later. Raspberry Pis are made in the UK. We have a factory, a Sony factory in Wales. They make all the Raspberry Pis in that one factory. They can make about 20,000 units a day when it's at peak. So originally the Raspberry Pi was made in China. We managed to move production to back into the UK, and we can kind of keep tabs on production quality, and it ends up being a sort of a quite lucrative way of doing it, in that we can reduce our costs and make it more cost effective to do it that way. We also released a compute module. This is for industrial customers to build a product around the Raspberry Pi. So instead of taking the original Model B in that form factor and trying to build something around it, which a lot of people do, and that's fine, we wanted to make something a bit more flexible. So the module along the bottom there is the same form factor as a SODIMM RAM chip, and it slots into a board like this. This is the one that we sell that's like a kind of demo board that you can use to prototype on. But the idea is that that's an open source board, and you can design your own I/O board that this Raspberry Pi's compute module chip slots into. And if you wanted to make a smart TV that had that essentially had a Raspberry Pi powering it. You could design your own board that had, you know, the HDMI and the Ethernet and the USBs and whatever else you wanted, exactly where you wanted it on the board. You can design your own and build your own product around that form factor. But you still have the support of the Raspberry Pi Linux kernel and all the device drivers and all that sort of thing that have been improved over the last 4 years of Raspberry Pi being around. Last year, we brought out a new revolutionary product, the Raspberry Pi Zero. I have one here. We reduced the cost of the Raspberry Pi down to $5 when we brought that out. So this is now our cheapest model. It's got the same chip as the Raspberry Pi 1, but it's overclocked to a gigahertz. Still a single core. So at this point, we had the Raspberry Pi 2 out, which had gone up to a quad core. This is still single core, but we've got half a gig of RAM on there. Made it into this new form factor, nice and small, really good for embedding, and really good for little projects. And then earlier this year, we brought out Raspberry Pi 3, which was a 1.2 gigahertz quad-core 64-bit CPU with the same graphics stack we had before. This has a gigabyte of RAM, but the price is still $35. So this is a kind of headline main product that we recommend for most general purpose use. And if you want to do something kind of interesting embedded, you don't mind having the lower powered chip, you can use a Raspberry Pi Zero, which is cheaper. We've sold over 9 million devices in the 4 years we've been running. We've had a few minor revisions and brought out different models, all the way up to the Zero and the Pi 3, the most recent ones. So we're sort of rapidly approaching 10 million, which would be a really big milestone for us. And all the money that goes towards Raspberry Pis, when anyone buys one, there's a little bit of money that goes towards the foundation, and we put that into our educational programs around the world. So the Raspberry Pi Foundation's mission is putting the power of digital making into the hands of people all over the world. So that's anything to do with programming, learn about computers, making things on screen or in robotics or anything like that. We're focused on giving young people the opportunity to experience that and learn from that. One of the ways we do that is, as I've talked about, is making these low-cost, high-powered computers. We keep making them either better and or cheaper, and they're used in education, which is our original purpose. Part of them are used in education. Some of them are used in sort of hobby projects, people making their own home automation systems at home, that kind of thing. But they're also, as I said, used in industry. So there are people building their factories that are monitored with little Pis because they can just buy one for $35 or less. Stick one in the corner, kind of this always-on Linux box that's really cheap to run. They're really handy for that sort of thing. And if you look at Raspberry Pis in schools, I think we're kind of solving two different problems. So you see the school on the right there. That's a school in London, and they have computers, they have interactive whiteboards, they have lots of technology, but they were in a system where they're running Windows and they're not allowed to install programming languages or any IDEs or any other tools like that on those computers because of the restrictions of the school. So even though they've got that equipment, they don't really have the power to use it. So putting a Raspberry Pi in front of that monitor and connecting it up with the existing mouse, keyboard, and monitor, you've actually given them a full programming environment computer that they can hack on, and they can do all those things in a sort of more safe environment that the network administrators would be happy with. And they can actually take that further and do kind of some of the physical computing projects, the hobby projects that I'll be talking about, that they wouldn't have been able to do on their Windows PCs. And then if you look at the next picture, this is a school in rural Cameroon. And there are a few of these in parts of the third world where they don't have computer suites. They don't even have textbooks and things like that in some of these places. And being able to get Raspberry Pis into those schools gives those, with some second-hand monitors, second-hand mice and keyboards, gives them the opportunity to just use a computer at all. And they can, even if it's just typing, they're learning typing, they're understanding the basic systems of how that computer's being processed, then it's giving them an opportunity they wouldn't have had. We do a lot of work ourselves, as well as just providing the computer for sale as cheap as possible so that other people can do great things with it. We do a lot of things in the foundation that we're kind of directly working on ourselves. We run a teacher training program called PyCademy. We've trained hundreds of teachers in how to get the most out of Raspberry Pi and how to accomplish teaching the computing curriculum that's been brought into the UK and in other countries around the world. We create free resources, so learning resources, materials for teachers to teach with or for people at home to learn with. And they're great fun to see people doing those little exercises that we've built at the foundation. We run programs. We've got all sorts of different programs that involve mostly involving young people and engaging them in digital making, in programming, and in building things. And we also we have another organization where we merged with last year called Code Club. They operate around the world, setting up after-school coding clubs in primary schools for age 9 to 11 to give them a good head start before they get to secondary school and they have to start doing programming. So that's a network-led volunteer program that called Code Club. So if we have a look at Raspbian, so this is the Raspberry Pi's operating system. It's based on Debbie and Jesse. It didn't always look like this, but this is a recent screenshot. So we've got a nice user interface now we've been working on. If you have a look at the menu and things, you've got a real kind of drop-down menu there with all your programming interfaces in. You've got a web browser, preferences shut down. It's supposed to be, it's not supposed to look like Windows or look like Mac, but it feels very familiar to people. So it's a very kind of welcoming experience, and it's been designed to be nice to lots of different users with different experiences. Physical computing. So one of the main things that's kind of really interesting about Raspberry Pi, as well as its cost and its small size, is the extension of into physical computing. This is a thing that a lot of people who've done programming before, they might have done some scripting, desktops, application scripting. They might have done some website stuff, things like that. But what a lot of people have never done before is done something kind of physical in the real world. So the Raspberry Pi has these GPIO pins, general purpose input outputs. It has a big bank of those pins along the side of the board. You can connect up physical devices to that board. So like here's an example of an LED wired directly to the pins. And you can program those pins to come on and go off. And you can have input devices and output devices. So you can read pins or set them high and low. Or you can have a breadboard and have all your components laid out on the breadboard and wire them up that way as well. Another way of accessing the GPIOs is through use of an add-on board. So there's all these companies around Raspberry Pi in the community and providing infrastructure to the Raspberry Pi community by making these add-on boards that sit directly on top of the Pi. So I've got one here. It's just a little board that's like the size of the Raspberry Pi, and it just slots on top of the pins. And it gives you access to some components that are soldered onto the top. So with these sort of things, it's kind of a ready-made something for you to play with, and there's all sorts of different things for different purposes. There's actually a specification that we made called HAT, hardware attached on top, and it denotes the size of the board and where the mounting holes go. So you can see this one down here. It's actually one we make ourselves called the Sense HAT, and it slots neatly on top of the Raspberry Pi and has the mounting holes sort of lined up so you can just hold it in place. So originally, programming this looked like this. So if you wired up an LED to your pins, you would use at the time the de facto standard library was called RPi GPIO, and this is a very low-level library, and it had lots of kind of boilerplate code. So so you have to import it at the top, then you set the mode of the board, because there's kind of two different numbering systems. It's very verbose with its warnings, so people generally tend to turn them off. Then you have to set up a pin so that all the pins are numbered. So I'm using pin number 17 there, and I'm setting it up as an output device. And then in a loop, I'm saying turn it high, sleep, turn it low, sleep. And I just continue, and the LED will flash, that LED will blink. This is very low level, as I say, so it's all about, you've got input devices, output devices, you can turn them high and low, and you can read the pins. And that's great because it gives you the flexibility to do anything you want to do with those pins. And there's for the sort of younger students, if they want to do something physical, it's a little bit daunting having to write so much code, even for the simplest example. So if you had a look at a lot of primary school teachers, the younger teachers of the younger children, would go to Scratch. So Scratch is a really popular programming interface for beginners in that they can drag and drop blocks into place. And they just learn about sequencing. They just learn about a sequence of instructions takes place, and they just place them in order. However, the way you interfaced with the GPIO pins from Scratch actually meant you had to do some kind of like programming inside these little broadcast blocks. So here it says broadcast GPIO server on, broadcast config 17 out. So this is very similar to what I was doing in Python. Then forever broadcast 17 on, GPIO 17 on, wait 1 second, GPIO 17 off, wait 1 second. So the same bit of code, very similar, but you still have to type in those commands and you have to get them right. And there's no error reporting. It just sends a broadcast that didn't do anything. So it's not ideal, this. And if you want to do something quite complex with a more complex sensor or something, a sort of more complex input device, then you've got to write lots of these broadcast blocks. So it wasn't really suitable for a lot of use. So I was thinking, what could we have that's something that's more approachable? A lot of teachers would say to us, Python's too hard to teach with, so we stick with Scratch. And then they end up staying in Scratch too long. They actually, kids getting up to beyond 11, 12, 13, even 15, 16, and their programming lessons in school are still in Scratch. And it's not really good enough if they're going to go on and do some, they can't really use Scratch to make any serious applications or anything like that. And they haven't gained the experience of dealing with a real text-based programming language. A lot of teachers would say that things like RPyGPIO, this library, and Pygame, you just have to write too much code to get going. Even the simplest examples, lots of code you have to write. And this is one of the reasons they wouldn't move on to Python, or they would only do very basics in Python. But because Scratch in GPIO was difficult, we didn't really have a good alternative. So, as I say, lots of problems with RPyGPIO. As much as you can do lots of great things with it, you can, because it has that unlimited scope of you can flip pins up and down and do all that sort of thing. There's lots of people just copying and pasting code they found them from the internet. This is how you use this sensor. They would paste that in. If they want to change it, there's quite a lot of code to sift through to find what you want to change. And very un-Pythonic interface. So not very good to encourage that sort of, that kind of style of writing code. So I actually ended up coming up with a new library. So this is a bit like what Jackie was talking about earlier, where you look at url-lib2, and if you want to do a basic web request, you've got to write a big load of code. But really, what you want is requests, which is where you just say request.get this URL. So I came up with a similar thing for GPIO, called it GPIO 0. In that it's zero boilerplate, or very minimal boilerplate. So in GPIO 0, every component is provided as a class. So you instantiate an object of a given class, like an LED, and you manipulate that LED object. So you don't have to keep remembering which pin number it was connected to. It's all part of the state of the object. So here's that example again. While true, LED off, on, sleep, LED off, sleep. That will blink your LED. Alternatively, LED.blink. This does some interesting stuff with allowing you to, so this actually blinks in the background, so it has a kind of it does the threading for you as well. So you can have your LED blinking, and then your next part of code might be, wait for a button to be pressed, and you're not blocked up by waiting for that while true loop to end. So it's a really handy feature. So if you look at LED, you've got, you create your LED in that simple way. All you need to provide is the pin number, and then forget the reference to that. You can turn it on, you can turn it off, you can toggle it, which will take it on to off or off to on. and blink will flash it on and off continuously. There's a few other options in there as well. You can blink it on for 2 seconds, off for 2 seconds, or change those numbers. You can bring it to the foreground, so if you wanted it to blink, say 10 times and then stop and proceed to the next line, you can do that as well. Buzzer is very simple, another very simple component. So it works much the same as LED in that you can turn it on and off, you can toggle it. The word blink didn't really make sense for this, so we use beep. So that beeps on and off continuously. So I was just playing around at this point, and I thought, maybe I wanted something here. Maybe this is like a good interface to how it would be good to program components like this. So I threw something together on GitHub and shared it with a couple of people. And one of my friends, Dave, shared some ideas with me, and he sort of got hooked quite early on, and he's been contributing a lot to the library. So if we compare RPi-GPIO's button interface. So if you set up this GPIO pin number 4 as an input, one of the things you have to do is tell it whether the circuit is pulled up or pulled down, and it's this complicated sort of, if you're trying to teach this to kids, it's certainly a complicated procedure to teach, in that is it wired from the ground pin to the GPIO pin, or from a 3.3 volt pin to the GPIO pin. One of them is pulled up, one of them is pulled down. The most common use case is pulled up, so this is what people do a lot of the time, and it's this. This means this mbit GPIO.pud up means pull up or down up. So all these constants that are used in the library to express all these different things. And because it's pulled up, that means that the pin is high by default and low when the button is pressed. So if you poll it, so if you kind of in a loop, you just read the state of the pin, is it high or is it low? Then if you've pulled it up, you have to negate that by saying if not GPIO input 4, because that means it's pressed. And then for pulled down, you change pud up to pud down, but then you have to switch your, you don't have to have your negation anymore because it's low by default, and then when it's pressed, it goes high. So in GPIO 0, you create your button, and in this case, this is pulled up. It's a default parameter that's set to pull up because that's the most common use case. And then the same example, polling in a while loop. So you say if button dot is pressed. So that's a property that reads the state of the pin and returns true or false. So that works exactly the same. And then if you want to pull down, the code beneath is exactly the same. The only difference is that I said pull up equals false. So I don't have to change anything about my code later on. I use the same code. Another way of dealing with input devices in RPi-GPIO is this function wait for edge. An edge is, this is another thing when you have to explain this. If you're teaching with RPi-GPIO, you'd have to explain all these concepts to the teachers or to the kids, when really you just want to say you've got a button, is it pressed? So wait for edge. An edge is where it falls from, if you've pulled it up, and the edge, when the button is pressed, it falls from high to low, and that's called a falling edge. And if you've pulled it up, then, if you've pulled it down, then it's a rising edge when it's been pressed. And so you're essentially waiting for that action to have happened, that event to have happened, and you halt on that line until that thing happens, and then you proceed. So this is another way of doing it. So you've got wait for edge because you've set it up as a pull up, then pressed means, falling means pressed. So you have to remember which way around it is. And then it's the opposite for if you've pulled down, then pressed means the edge was rising. So in GPIO 0, that's just you set up your button, you haven't told it a pull direction, so it's pulled up by default, but it's just wait for press. And then if it's pulled down, it's still wait for press because the state is hidden inside is encapsulated within the object. You can also do callbacks in RPi-GPIO. So you create a function that takes in a single parameter, the pin number, and you say GPIO add event detect on pin 4, a falling edge, and this is the function. So you pass in the reference to the function that you want it to call when there's a falling edge detected. And in GPIO 0, you can do the same thing, except we use this property, the setter property, button.whenPressed, and you pass in a reference to that function. So you're saying when the button is pressed, run this particular function. And there's also when released, which is the same as doing the opposite in your your edge detection on your event detection on falling or rising edges. So there's when pressed and when released. In that case, I didn't refer to that pin parameter that's passed into the pressed function because it always passes it in by default. But in GPIO0, we don't need to do that. But if you want to access that, say if you set up multiple callbacks with all passing to the same function, or calling the same function, and you want to look up, like if they, okay, so there's two different button presses that both call this function, but I do different things according to which one it actually was, then you can pass in the pin number. So you would do that, and you can say print the pin number that was the one that actually called me. And you can do that in GPIO0 as well. If you pass in, you actually pass in the button object rather than just the number, and you can use that button object itself, or you can look up the number like I've done there. If you've got two components, like a button and LED, so you've got an LED is an output device, button's an input device, as well as making my own custom function to say print hello when the button is pressed, I can refer to another function available in this case in GPIO0. So I can say button when pressed, LED on, and when released, LED off. So I've just passed in those references to those functions, and it stores those. When there's an edge detected, then it runs those callbacks. So as I hold the button down, the LED is on, and as I release, the LED goes off. There's another thing you can do in RPi GPIO using PWM, pulse width modulation, which is a way of you can set the brightness of an LED. So here's an example. It's kind of an obtuse syntax, and it's not very similar to the rest of the library. The library is very procedural, and you just use a series of function calls. And in this case, there is actually a PWM class which you have to create an instance of, and then you manipulate that object to change the frequency. So change the duty cycle. So in this example, you have to say, you create your output device on a particular pin. You create your PWM object on a particular pin at a particular frequency, and then you have to start it at a particular frequency. So if we start at 0, that will be off. And then you can change the duty cycle to set it between 0 and your frequency. So you can set it between 0 and 100, and you set the brightness according to that. PWM in GPIO0 is just a different type of LED class. It's a PWM LED. You can still use the on-off methods, but you can also set its value to a float between 0 and 1. So just a really simple way of setting a brightness to in this case, a half. And as well as, you can still blink a PWM LED, and it will blink regularly, but pulse is one that kind of fades in and fades out. So you can kind of do some interesting sort of siren effects with that. If you've got you can get a full color LED, so which essentially just has 4 legs instead of just a ground and a single, an anode and a cathode leg. You have a ground leg and then 3 that go to the GPIOs that you control the red, the green, and the blue LED inside the case. You can access LED.red, and that's like a LED object. It's actually a PWM LED object, and you can manipulate that, turn that one on and off. You can set the color or the value of the whole object as a 3-tuple, and you can set the value of individual LEDs as well. So you can use that to tone up and down the color that you get out of your full color LED. Another device like this is traffic lights. So you can just have 3 regular LEDs, maybe all on a breadboard, or you can buy these little components which have 3 LEDs in that, the red, amber, the green, in that kind of configuration. So you just create an instance of a traffic lights object, giving it the red, amber, and green pins that it's connected to. You can turn them all on, all off with on-off methods. You can control individual lights as well, like lights.red.on, and you can toggle the whole thing, so it will flip them all around. And if you want to do a traffic light sequence, this is one way of doing it, where you access each individual LED, turn them on and off. Or you can set the value as a 3-tuple. So you can go through the sequence like that. The hat that I showed earlier, this one, is a board that has 3 LEDs, a button, and a buzzer. So it's just a really simple hat. Some of the hats are sort of more complex. They'll have their own microcontrollers and things like that to control more advanced components. But because this one's quite straightforward, it's really easy to add to the library because it's just a case of having all those components that I'd already added in a sort of composite device. So with that, you've got you create your instance of traffic hat. You've got an instance of traffic lights. It's just a traffic lights object. You have a button and you have a buzzer. You can refer to all of those. And if you want to use PWM on those LEDs, there's just a keyword argument, PWM equals true, and that will that will allow you to control the brightness of your LEDs as well. And that's quite consistent throughout the library that you have all these similar features. A motion sensor is a more complicated input device in that it's quite it's not just on or off. You can have you basically keep checking it in the background and read it, and then you do some checking on how many times it was high, how many times it was low, and you can set your threshold and things like that to determine whether it's a passive infrared motion sensor, the sort of thing you'd have in the corner of a room that detects whether a burglar alarm should go off. But then with like the button, you can do it where you did when pressed and when released. You can do when motion and when no motion, and you have is motion, is no motion, and all the same sorts of methods and properties that all input devices have. So you can set when motion, turn the LED on. When there's no motion, turn the LED off. And similar with a light sensor, you've got the third one I was talking about is the wait for light and wait for dark. So your motion sensor would be wait for motion, wait for no motion, which is your wait and block at this point until there's motion and then continue. But if you want to do have these event detection set up in the background while something else is going on, then that will you do that with when motion, when no motion. Motor. So a motor is comprised of two GPIO pins. If you put one of them high, one of them low, it will go in one direction. The opposite way around, one low, one high, it will go backwards. And turn them both off, and it will stop. So rather than having a series of flipping certain pins high and low, you just say motor dot forward, motor dot backward, motor dot stop. And then similarly, if you've got two motors together controlling two wheels, you've got a robot. So if you, again, rather than having, turn this one high, this one low, this one low, this one high, this one low, this one high, this one high, this one low, and doing all the different combinations for different states the robot should be in, it's all wrapped up in robot dot forward, robot dot left, robot dot right, robot dot backward, and stop. And there's also pre-configured robot interfaces. So if, here I've passed in left. The left motor is on pins 17 and 18, and right is 22 and 23. There are some kits that are available that are just they have pre-configured pins. So by name, I've just added those as wrappers around those classes, so you don't have to look up the pin numbers. If you want to create, this is a kind of a simple example of using buttons to control different things. So you've got 4 buttons, left, right, forward, and backward, and they control the direction of the motor, of the motors and the robot. So you just say when the forward button is pressed, the robot goes forward. When it's released, robot stop, and do that for each of them. And you've got a simple kind of controller for your robot. So Pi camera, the Raspberry Pi camera module is an interesting one as well. This isn't. There's already a library for this made by Dave, the guy who's been contributing a lot to GPIO 0. So he made the PyCamera library. So there's no need for us to add that into GPIO 0 as another component, but they work very well together. So the way you use PyCamera is very similar. You create an instance of a PyCamera object that I've called camera, and camera.capture and then a string will capture a picture, a still image, and save it in the location you provided. So here I've got two GPIO 0 buttons. I've got one called left, one called right. When I press the left button, the preview starts, so I see the preview on the camera. When I release it, it stops the preview, so you can just hold down the button as long as you want the preview to be on the screen. And then the right button runs a custom function called capture, where it just looks up the date time and calls camera.capture with a path to the Pi user's home directory and names the image according to the date timestamp. And if you want to do stop motion, so every time you press the button, it goes around a loop and captures an image, increments the number, saves it, and you've got yourself a batch of images that you can turn into a stop motion movie. So the Raspberry Pi has no native analog pins. All the pins on the Raspberry Pi are digital. So if you're used to programming an Arduino, because that's a microcontroller, they have direct access to analog pins. But the way you can achieve reading analog devices like potentiometers and sensors and things on a Raspberry Pi is using an analog to digital converter. So one of these ADC chips, place that on a breadboard and wire it up to the Pi, and it uses the SPI protocol. You can wire up, so with this particular chip, it gives you 8 analog input pins that go over the GPIOs, but using the SPI bus. So you create an instance of something connected to that MCP308, the name of the chip. That's the ADC. And in this case, I'm referring to channel 0, so that's the default, is if you're just using the first channel, you don't need to provide it. So I'm creating an instance of a pot, a potentiometer, on that device, and if I just access .value, then I see a number between 0 and 1, and I see wherever you turn that dial to, it'll be, you'll see in your loop it changing between 0 and 1. If you wanted to use that to control the brightness of an LED, you just pass, I was playing around with this code, and I just tried this. So while true, set the LED value to whatever the pot value is. So as you turn your dial, your LED goes, changes brightness. And I thought, I could do this with an RGB LED, a full color LED, where I have 3 different potentiometers, and I dial up the red, the green, and the blue, and it changes. I can mix the whole color using this. And I kind of thought, this is a pattern here. There's something interesting here where I'm stuck in this loop where I'm having to constantly update the values. And I really want to just be able to say, I've got a potentiometer and I've got an LED. They should always sort of match each other. So I went onto our GitHub, and this was issue number 76, title while true led.red equals pot.value. And a lot of the library was built on me asking kind of dumb questions like this to my fellow maintainer, Dave. And we would just have a chat about something, and every decision made about what the API should look like, or what we should implement, what we shouldn't, how things should work, was all developed on here, and you can go and read the history of it. So I said, would it be possible to automatically pass the value of potentiometer directly into something like an LED or an RGB LED? So that this example, the one I just showed, could be done automatically somehow. I.e., when the pot changes, the pot value changes, the LED changes accordingly. And honestly, I closed this tab before I hit submit and thought, it's a stupid question, I won't bother. And then I thought better of it and went back and hit submit. And Dave came back saying, I might be able to do something. It's not really going to be as nice as this, because it's kind of expecting this single scalar value. But then he had this idea that he could do something cunning with involving iterators. And he explained his idea, and he was like, I've done it, this is amazing. And he explained the idea and said, that you can now do this. And I said, Dave, this is amazing. So now we have this this thing where every device, whether input or output device, has a dot value property, and you can read its current value. So if it's an input device like a potentiometer or a button, it might be 1 or 0 for a button, or a potentiometer could be anything between 0 and 1. And if it's an LED, you can still read its value, but you can also set its value. So you could turn an LED on to half brightness by setting its value to 0.5, or then you can read the value. So what he added was that everything has a dot values, which is an infinite iterator constantly yielding the current value. And what that means is that you can, it also has this thing, an output device has a dot source, which means where do I get my values from? And it's a really clever thing that means you can take an input device, pass its dot values iterator into the source of an output device, and they're now connected like in a background thread. So now you can just have led.source equals pot.values, and those two are now connected. So as I dial the potentiometer, the brightness of the LED changes straight away. So I'm not stuck in a loop. I can still do other things, and those two are now connected in the background. And for color mixing, like the example I had before, instead of doing while true and setting them all individually, I can set all the sources of each LED like that. Or I can even just set the whole source of the LED, like the whole, all three components of the LED, and zip those values and pass that in. Another thing you can do with this is you can write your own custom generator. So that could be one that could go on forever, or it could be just one that has a kind of a lifetime. So you can write your own generator that just goes, while true or fry in some range, and yields a value, and then that just constantly updates the source. You can set the source delay so that it does, say, every 0.1 of a second or whatever you want it to be. So you could do something like this. So if I create a PWM LED and set its source delay to 0.1, so 0.1 of a second, I can then set its source to just this generator that I've made, and it just goes up slowly over time, so in steps of 10,000ths. And slowly, over that long period, will get brighter, according to that source delay. Another way you can do it is bring back your input device. You pass your dot values from your input device through a custom function of your own that manipulates that value in some way, and then passes it into the source. So if you want to create your own function, say, read slowly, and it just does that source delay thing, essentially, and yields the value each time, but sleeps and comes back round. You set up the source to be, you pass in sensor.values to read slowly, and it will pass them in one at a time. And then we introduced something called, actually into the library. So previously you had to write your own functions like this. But now we have a set of commonly used source tools. So things like invert, and, or, and even things like cos and sine and random, and some really useful ones like that live in source tools, where you pass your values through one of these tools, these built-in functions, and then into the source of an output device. So then you have something like this. You've got an LED and a potentiometer. You import from GPIO0.tools import inverted. So that just takes something in the boundary of 0 to 1 and inverts it from so it's the other side. Then your LED source would be inverted pot values, which just means rather than left, the more left it is, the brighter it is. It goes the other way. That's a simple example. And then we added some other components, which are composite devices. So LED board is just a generic class that allows you to create a collection of LEDs. So you give it a bunch of pin numbers, just any amount of pin numbers, and it creates LED objects on all of those pins. And there are lots of niceties in the library like this, where you can just, the whole class is iterable. So you can just say for each LED in those LEDs, in that LED board, turn it on, so you access each LED individually and sleep. And then you can still control the whole LED board by doing LEDs to on or LEDs to off. There's even some clever stuff where if you, it maintains a sort of ownership of different blink threads. So if you've told one of the individual LEDs to blink, and then you tell the whole thing to blink, then it sort of overrides those, the ones you set it before and stuff like that. Kind of maintains that for you. Another way of using a collection of LEDs is using LED oh, there's a mistake there. Top line input is wrong. LED bar graph. So you create your instance of LED bar graph, again with any number of pins, and rather than just being able to iterate over them, you set the value of the whole thing. So if you set it to a half, it will turn the first half of the LEDs on. If you set it to minus a half, it will turn the end 3 LEDs on. Set it to a quarter. In this case, I've only got 1 out of 6 because it's rounded down to 1. But if you wanted to have some more precision, you could use PWM equals true. Then you have, it basically goes 1, 1, 1, 1 until it gets to the fractional bit and sets the brightness on that one, which is kind of cool. So at some point as well, we also looked at how we could support multiple backends, because originally in the first sort of the first major release, we were all it was just a wrapper around this existing low-level module, RPi-GPIO. But we looked at some of the benefits from some other libraries that were less popular, but did certain things particularly well. So RPi-GPIO does software PWM, so everything is it's actually done in Python, so it's prone to being held up by by CPU, by jobs in CPU. So RPIO is another one that used a DMA controller to do it sort of slightly more emulated hardware PWM. There's another one called PiGPIO, which is a really cool thing. It runs as a daemon, and the daemon runs as root, but you can talk to it. You can talk to it directly, and it will do the instructions you give it. PiGPIO has a massive extent of all different types of GPIO, I2C, SPI, all these different protocols that it supports, and it seemed like a really good option, so we added that as well. But then we also have a fallback option, so if there's no libraries found, it goes to the last option, which is a pure Python implementation of flipping the pins up and down that Dave wrote. This native thing, it's not very well supported, and it's not recommended you would use it. It's very slow in CPython, so not very reliable. But it's surprisingly good if you're using PyPy, so it's kind of an interesting experiment there. One of the great things about PiGPIO, the third option I showed, is that it actually has a remote support, and it works over sockets. So you can do this locally on a Pi, or you can even do it remotely from another Pi or another PC. So in this case, I could install GPIO 0 on my laptop, my Ubuntu laptop, or a Windows machine, or a Mac. I can install GPIO 0, the Python library, because it has no dependencies, in case you want to use it like this. You can create an instance of an LED, but referring to a PiGPIO pin, pin 12 on this particular IP address. And then you can control that like it's on your own device, and you can just call LED.blink. So there's some really powerful stuff you could potentially do with that. I mean, if you've got one Pi and you want to have access to a whole other set of GPIO pins, instead of using 2 Pis and having them talk to each other, you just sort of borrow the pins of the second Pi and control everything from a single Python application. So GPIO 0 kind of happened quite quickly. So in September, I had this initial idea where I was giving some talks, and I was talking about showing teachers how they could do abstraction, basically, because these libraries were so verbose and had so much boilerplate. I was going around showing teachers, right, if you create little files like this, you can get the kids to import them, and I started building like LED classes for them and stuff like that, and showing them how to do this. And I just thought, this is silly, it should just be a module. So I started it the 14th September, initial commit on GitHub, shared it with a few people over email, and they piped in on a few GitHub issues. We named it GPIO 0, referencing Pygame 0, which is a 0 boilerplate wrapper for Pygame, which is really cool. So on that date, we had our first pull request. That was from Dave, and he's contributed loads to the library since then. We released the first alpha and released it on PyPy. End of September, we had version 0.6, which was the first public beta. So I was actually sending that out to teachers and asking them to try it out and give me some feedback. We had a couple more, got to 0.9, that was the fourth public beta, and it was finally released on my birthday, the 16th of November. That was version 1.0. We got it straight into the Raspbian image. So I showed to Eben Raspberry Pi and said, I've made this library. What do you think? And he said, this is great. Let's put it in the standard image. So everybody who downloads Raspbian from the website now gets this GPIO 0 library. We did a couple more releases since then. We've added some components and added some of the source tools and some of the various backends. We added those in those releases, and we're working on 1.3 now. But so at version 1.0, we had 200 commits. There were pretty much just two contributors. It was me and Dave. About 4 people had filed some small documentation issues and things, but all the code was written by me and Dave. We did this all over the course of all our conversations about the API design, and every decision was in a GitHub issue. So there were 103 GitHub issues. So like 1 for every 2 commits, we had a different issue, which probably had several comments on the conversation. 53 issues, 50 pull requests. 4 alpha releases, 4 beta releases, and it was just 68 days between initial commit and the first major release. 1.3 is a work in progress, so there have been quite a few hundred commits since, I think like over 100 commits since 1.2, so we should try and get something out soon. We've now had over 500 commits. There are 5, I'd say, major contributors who've given significant things to the library, which is really nice, but it's still mostly me and Dave. In fact, I'd almost say mostly Dave. And the minor contributors up to about 8. There are 390 GitHub issues, 178 issues, 212 pull requests. So it's still really healthy and really conversational. Lots of people I'm seeing in the community using this and getting a lot of feedback from them. In future development, so we just always want to add more components. So there's more interesting components out there that we don't support. Most of the components we have are very commonly used. So things like button, it's not a specific type of button. They're just really generic components. But we definitely want to sort of anything else that we find out there that people are using that isn't supported. The first thing to do is show them how they can do it using the underlying classes, the generic input device and output device classes. And how to use it that way, but then to add support in later versions for the more interfaces for those components. We're probably going to move the default backend from our PyGPIO to the PyGPIO daemon once we sort of have some certainty that it's as well supported. And it's really interesting to see the remote GPIO support. It's a really cool feature, and I think it'd be good to have more examples of how to use that, especially in schools where they perhaps can't plug in a Raspberry Pi and have all that system set up. If they can just have, say, a Pi 0 that was on their network that they could control from their Windows PCs that are already set up, then it kind of gives them the best of both worlds. And it would also be interesting I'm not sure exactly how this is going to go, but I want to find a way of promoting use of a GPIO 0 standard so that other people can create their own libraries that have classes that fit together with GPIO 0 classes. So if you create your own type of, you have your own sort of more bespoke LED thing that's like an RGB, a special RGB LED, that it could have the dot value and the dot source things, so you could plug it into these other components and do some of this interesting stuff. A lot of people are making that make hats and make add-on boards. They have their own Python libraries, which is really good, but they're often quite similar to our PyGPO. They have that verbose nature, lots of boilerplate and sort of awkwardly named things. So it'd be definitely interesting to see if we can do something there. So if you've got a Raspberry Pi, like in your drawer at home or something, you want to give this a try. either update to the latest Raspbian Jessie image, it's been in there since November, or just upgrade your old card, just update your sources and install the Python 3 or Python 2 version. The documentation is on Read the Docs, gpi0.readthedocs.io. The installation instructions, API documentation, and more importantly, we have a page called Recipes, which is just all the sorts of things that I've been showing you in the slides, just those bits of starter code that show you how to actually use something. Which is, if it's teachers and kids reading this, then they need to see code that works rather than figuring it out from the documentation, from the API docs. And it's on GitHub, and there's, as I say, a really vibrant community of people that contribute comments on GitHub, and that's how all the decisions are made. So if you want to know why something acts like it is, it's probably been determined by us having a conversation on GitHub. So do check that out. Any feedback on using it in there as well, and suggestions or bugs or anything, do feel free to file them on GitHub. Contact me, Ben at raspberrypi.org, or Ben_Nuttall on Twitter. And a lot of people are using the GPI0 hashtag to share their projects and their interesting code and stuff. There's this kind of movement at the moment to create more libraries like this kind of zero boilerplate, really easy to get going kind of library. So Pygame0 was the original one, and that is entirely zero boilerplate. A guy called Daniel Pope created it, and he actually, rather than just being a module that you import, he's taken it a step further and made a runner for it. So rather than running Python mygame.py, you run pgz run mygame.py, and even with an empty file, it opens up a blank game window, and you just add like one line at a time, and you get something significant sort of with really small steps, which is really cool. I haven't gone all the way with that with GPI0, but it's a very simple, just you import the names of the components you want to use. So there's GPI0, there's a guy working on Network 0, which is a way of doing simple networking between devices, so teachers can teach how communication between devices works. And there's a Bluetooth library called Blue0 that's being worked on as well, that just, a way to make that really simple to get started. So they're all worth checking out. And if anyone's got any libraries like URL-lib where they think, it should be easier than this, I should make requests, I definitely recommend you have a go. There's definitely a call for it. It's a bit like this kind of such and such for humans type thing. So it's really worth taking a look at that. So how can you get involved in any of the stuff I've been talking about? So take a look at the Raspberry Pi website, raspberrypi.org. We've got daily blog articles on there, news projects and stories. The operating system downloads are available, so we release a new Raspbian image every 3 or 4 months or so, with new software and updates. Help pages, documentation, community sites, and forums are all on there as well. We have a page of learning resources, so we have an education team. A lot of them are ex-teachers. I've contributed a lot of these resources as well. So they're Python projects, Scratch projects, all sorts of different things. Some of them are using GPI0, show you how to use these components and things and make little games, little interfaces. Raspberry Pi Weekly is a weekly email newsletter that I run. News projects and articles every week in an email. And you can read that on the website. We have a magazine called the Magpie, which was originally a community magazine, which was a free PDF download. It's now the official Raspberry Pi magazine, and we sell it in UK shops and US shops and online. But it's still a free PDF download, so if you can't get it from the shops or you don't want to get a subscription, you can access the content for free online. Occasionally comes with a free computer. That's how we announced Pi0. We stuck that on the front of the magazine, and it was like a free gift, the way that computer magazines of the 80s used to give away floppy disks and later CDs and things. We gave away a computer. We also do a book series as part of the Magpie publication. So there's books on learning Python and things like that you might want to recommend to people learning. I'm really interested to see if anyone wants to set up some community events in Russia. I don't actually see any on our map So people submit their events to promote them on our website. I don't see any in Russia at the moment. There might be some going on, and there's just a language barrier that they're not promoting them through our site. But it'd be really cool to see some community events, being set up in Russia, so kids and young people have the opportunity to get involved in this stuff. Take a look at raspberrypi.org/jam, and you can contact me for support in helping set up an event like that. If anyone's interested, do come and speak to me. And also, I mentioned Code Club earlier, which is our other project. So this is not really related to Raspberry Pi, in that not related to the hardware. It's just a program that the foundation runs. It's mostly things like Scratch projects, simple HTML, simple Python projects that they can do on their computers in school, usually on Windows. It's for 9 to 11-year-olds. They run around the world, volunteer-led. Anyone can sign up and register to be a Code Club volunteer. You just go into a school once a week, do an hour, teach the kids some Scratch. You learn it, the week before if you've never done it before. And you can talk to me about that as well. And if anyone knows anyone who would be interested in kind of taking a bigger step in actually running a countrywide thing as part of for Code Club Russia, that would be really cool as well. So there's plenty of ways to get involved, and I hope you found that informative. Thank you.
Thanks, Ben. Any questions?
Thank you for a very interesting talk, but just one moment isn't clear to me from your slides. When you showed an example for things like onPressed equals LED.on, what makes LED light up when this button is pressed? Is there some loop that pulls the button or some kind of background thread? It's not evident from the slide.
Okay, so in RPi GPIO, this was possible as well, and it's essentially just using the same functionality. There's a system-level interrupt in the Linux kernel that sends you basically say, I want to know when this event happens, and GPIO events are something you can monitor. So it comes in like that. So like kind of Linux kernel level, that's what it's doing. In terms of the Python code, there's a background thread watching for those interrupts, and it runs you basically pass in a function reference. It stores that, and it says whenever there's an interrupt, it goes look up what function I'm supposed to run at this point, and you can do one for pressed, one for released, and it saves them both. You can set it back to there being no event by just setting it to none. One unfortunate problem with that is because you're used to, if you're taught, right, you create your LED, you go LED.on, open close brackets, and that's how you call the method, that's what you do. And then you're told, if you want it to do LED.on, you don't use the brackets, but people do. So what they do is, they end up assigning it to none by mistake, because it ran, in fact, in that case, LED on would turn the LED on straight away, and then set the action to none. Or if it's blink, then they'll see it blink, and it'll be blinking, but they haven't pressed the button yet, and things like that. So it's kind of hard to point out what. It's also quite hard to describe what that is. The way I would say it would be, if I was explaining it to you, it would be very different to explain it to a child. But if I was explaining to you, I would say you pass in a function reference. That's a little too advanced to explain to a child, but I would say you give it the name of the function you want it to run later. I'd kind of explain it in that kind of a way.
Sure. Okay, thanks, Ben.